Today we have IMO 2025, problem 6. I won't be discussing problems 4 and 5, unfortunately, just because I didn't find those problems interesting enough, and just because of the lack of any ideas behind the problems. I just didn't find anything useful about them or interesting, so I won't be making the videos about them. And the problems that did have me interested was problem 6, which was the hardest by far, the question on the contest. And I'm going to walk you through the solution and how I solved this question and how I thought about it. And yeah, we're cutting out the whole intro again, but I'll make sure it's useful for you guys and you'll find out something new throughout this video. Okay, so here's the problem. We have a 2025 by 2025 grid of unit squares, and Matilda wishes to place on the grid some rectangular tiles, possibly of different sizes, such that each side of every tile lies on a grid line, and every unit squared is covered by at most one tile. And we need to determine the minimum number of tiles that Matilda needs to place such that in every row and every column of the grid, there's exactly one unit square that is not covered by a tile. So, the way you kind of want to approach this question is first get the answer to prove the bound. And I always recommend to start from bounding. Not from bounding, but just from getting a feel of the question by looking at small cases and trying to figure out what's happening. So let's just look at, before we do any observation, just look at small cases. So let's suppose n equals 1, where n is the side of the square. Then we want this square not to be covered, so the answer would be 0. So let's label the answer k. So k will be 0 in this case. Because we don't need to cover anything, everything is already done. Now, the other case is we need to do 2 by 2. And the funny thing about 2 by 2 is the only thing we need to know is when basically you cover these two squares. So you'll need at least 2 rectangles. So, and then we move on to 3 by 3. And there's a couple of observations you need to make about 3 by 3. So, first of all, let's draw the board. And it's not very nice. Just fix it a bit. This. That seems a bit better. Okay, we have a 3 by 3 board, and there's actually like two cases in which so crosses are basically the points, the unit squares that we don't want to be covered by a tile. So there's actually two methods to cover that. So it all brings down to the fact that there must be one cross in a corner, because without that there's contradiction. And so then we're just left over with the 2 by 2 square, and then you get all like this, which gives you 1, 2, 3, 4 as answer, or like this, which also leads to 4 as the answer. So we do know that for n equals 3, the answer is k equals 4. Okay, and now we move on to a 4 by 4 board. So let's start with the 4 by 4 board. And this is, I think, the crucial problem, and I'll explain it why shortly. So the first thing we notice is that so far there's not a lot of information we can extract about the answer. We do see that the answer is 0 to 4, so we might suspect the answer to be 6 next and just get a line here. That's what I thought. So another thing that we do notice is that here, when we look at cases in 4, and this will be a bit crucial, is that if we look at the corner, if there's a cross in the corner, essentially we do force a +2 because for every splitting of the 3 by 3 board right here, you kind of need to have these two and then here plus something else. So essentially, if you put a cross somewhere here, you kind of do note that there's no possible way of getting less than 6. And the other case is that what if we don't do that? Well, if you don't do that, there's actually only one case how you can, or not one, like there's this type of thing, which just doesn't round up nicely. And there's a more symmetrical approach, which is this. And here you actually notice that you can do it in 5. So if you do like this, this, and this, you can get n equals 4 and force it to be 5. So we do see some inconsistencies with the answer. So 0, 2, 4, and then 5. So that's a bit inconsistent. And the way I tried to approach it is I said, okay, well, if the answer is dependent solely on n, oops, sorry guys. Okay, so if the answer is solely dependent on n, then we might suspect it to be something like a polynomial. So, and if it is a polynomial, it's probably not more than degree 2. So, and you can just check by brute force that with these values, you basically can't get, you need to get a very weird polynomial. And that, like, if you try to work it through n, so demonstrating what I mean, n equals 1, k equals 0 means that k should involve like n minus 1 in it. And then you know that n equals 2 and then k equals 2, so you kind of assume it's like n minus something, so say n equals 2, then this 1, so you might assume n plus 1, right? Or, one sec. Yeah, just n, because n minus 1, n. And then you look here and it doesn't work. So there's no kind of polynomial that goes 0, 2, 4, and then 5. That's the basic thing. So this case is kind of special because you can't do any kind of trick like that in here. And so from this, you kind of have to assume, and that's like the first leap of faith, is that the answer should be dependent on n, but not on all n. So what I mean by that is like, since not for all n, the answer will be nice. And based on your experience of solving EGMO 2025 P6, the key is that, well, 2025 is a square. So, and that's kind of like an explanation why n equals 4 generalizes nicely and n equals 1, but these two don't. So, and now we're trying to find another polynomial such that for n equals 1 is k, and then basically for n equals 2, because we kind of look at 1 squared by 1 squared, 2 squared by 2 squared, so like wards of shape n squared by n squared. We're looking at this kind of force. So, and for n equals 2, we know that the answer is 5. And we probably guess that it's a polynomial again. So the answer is always should be a polynomial. That's kind of like the takeaway. The first takeaway that I was trying, like, if you don't know the answer, but you know some answers for small cases, just try to use it like just try to force it as a polynomial and try to guess the answer by trying to substitute it into polynomials. So what I mean by that is basically, let's say, first of all, another observation is we can always do at least 2n squared because in every row there's like at most 2 gaps, and in some rows there's like 1 gap, so we can do at least this. That's the first takeaway. And the other one is it's probably more than n squared as well, because we can't get more than n squared for some logical reasons. So the answer is somewhere between here. Yeah. So from here, we kind of can also see that it's probably like a polynomial of shape n squared plus ax plus b, and not like kn squared, just because of the bound on top by 2n squared. So it's probably n squared plus something rather than 2n squared plus something. And so now after you do that, you can say, okay, n equals 1, k equals 0, so the polynomial of your answer should involve n minus 1. And then we also know that for n equals 2, the answer is 5, so you get like this. So, and this is our answer if it's a quadratic answer. And linear obviously won't work, so we do know that for n squared by n squared board, we do need to know that this is like squares. So essentially, somewhere in the formula, you'll probably need n, which is another reason why this might work. So the final answer is like that we predict is this. And now we just need to show it. And here, the other trick with generalizing now. So here we want to generalize this into an n squared by n squared board. So the way you kind of generalize this stuff is you try to essentially look at variables. So here we have n equals 2. Look at anything that's 2 and try to change that into n. That's like a general advice on all construction problems. That usually works out pretty well. So in the case of n equals 3, what you want to do is just try to replicate the same trick as there, but with a 3 by 3 board. So the first thing we noticed in the upper construction is that we had like a big 2 by 2 square in the center, and then we had like these blocks arranged in like 2 by 1, 2 by 1, 2 by 1 in a kind of diagonal way. So if we go here, this will take a while, sorry guys. So here's our 9 by 9 board, and what ends up happening is that we want to fill it up in a similar shape. So then we can start testing. So we know that this square, it kind of starts from here and it's somewhere in the center. So we probably want a 3 by 3 square and some tiles as well. And what we notice is that we kind of want to generalize some stuff here. So we want to, if we drop a square randomly here, we basically see that the way the crosses are formed are like in this pattern, like this. So then if we attach another square like this, it kind of turns out that this pattern is pretty nice. So you get also some stuff like this. Yeah, and squares like here. So this generalizes pretty nicely. And now the only thing you need to do is kind of like work nicely with arranging all the squares into the right places. And the actual way to do it is put one square in the middle and then do the following. Start moving like this, I assume. Something like this. Wait, this, like this, like this, like this, like this, and like this. Okay, and from here you go like this, and you just fill up the whole board with 3 by 3. And after you get this example, it's kind of easy to generalize the whole thing. You just need to um, basically the other nicer way is kind of to think about it is like an infinite board of 3 by 3 squares like this. So I'll just delete this and delete this. So you kind of can think about it like an infinite board of a repeating pattern like this, and you just take out a fragment from it. So, but essentially the whole pattern is repeating. So this is a repeating pattern, but you just take a fraction of it. just some extract. So that's how you basically construct, and after you look at this, you can verify that the answer is this. So using kind of the answer, you could get closer to bound by thinking about there's one square here, it covers four, so the answer should be that, and just try to calculate and make your way through the answer. So having the answer sometimes helps you. Here, not as much, but the whole technique of me guessing the answer just by using polynomials and two values, that's a very nice trick to know when guessing the answer, because in some cases when you guess the answer, constructing the construction goes much easier, not in this case but just in general. And the other tip to take away from building constructions is try to look for anything that involves like the induction you're doing it on, and trying to generalize it. So here it was like a step 2 by 1, made it into a 3 by 1 step, 2 by 2 square, 3 by 3 square, so on, so on, so on, so on. So now we need to do the bound. So, so this is the part where actual combinatorics come in. So, okay. So we draw this board and we're trying to have, we basically have uh, certain crosses at some point, and we're trying to make everything work out. So we kind of have this whatever amount of crosses, and we're trying to fill out the empty spaces with squares. So with rectangles. So here comes, so let me just draw the board nicer. So I guess I'll just get rid of the blackboard. I'm sorry guys, I know you like it, but let's make the square board. And then let's make a 16 by 16 square. 1, 2, 3, 4, 1, 2, 3, 4. That's 8, right? Yeah, that's 8. And 1, 2, 3, 4, and 1, 2, 3, 4. So we do have a 16 by 16 board here, and what we're trying to do is we have different, just different squares here, 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 I don't know, here, this, this, like this, and like this. Or maybe it's better to do something like this. Okay. This, and which one are we missing? This line. Okay, we have our board. Now we're trying to find the minimal amount of rectangles we need to cover this. And we're trying to show that it's more than n squared minus 2n plus 3. Okay, so, and here comes a very, very common idea in boards, which I call lasers. So the laser method um, it essentially is a double counting method, but named cooler. So a lot of times in board problems, you have like when you have 1 by 1 squares, you want to launch 4 lasers from all the other sides, and the idea is you want to count how many lasers get out and how many points of other rectangles they intersect. So essentially, in this case, when we cover everything in the board, what we want to know, and this was my idea, is we want to know how many touching edges you have between rectangles and the other points. So essentially, if you cover all the edges between these points and rectangles, you're kind of done. And that's how you like intuitively understand what's going on. So the best way to think about it is by adding rectangles and seeing how many common points do they have with the crosses. And of course, there's an easy bound on less than equal to 4. And from there, you kind of get the idea that the bound is about n squared as well. So if when you were constructing the example, you had some troubles with that, you can, and you start doing the bound, which is sometimes useful as well. This is another signal that's about n squared. So, and here's the main thing in this question. We see this board and we're trying to calculate some edges. But there's another key observation that we need to make before we kind of get through this board analysis. And this observation is that essentially everything revolves around. So the only reason why the bound is kind of tricky. Oh, wait, we need this instead. So the only reason the bound is kind of tricky is because of 2n. And we will have to make a bound somewhere, so we'll have to make some sort of inequality in the process. And 2n is a kind of hint that you might need AMGM. So we do know that if a plus b equals, if ab is equal to n squared, then a plus b is more than equal to 2n. So that's kind of like a little hint, but it does end up helping us quite a bit. So essentially, what we want to bound is we want to get some sort of thing like this. That was my key idea. So when you can't work from the front, try working from the backwards. So for example, when I was stuck about thinking how to get the answer, I worked from the back. I assumed that the answer is polynomial, and I deduced something about it. So here we don't know the bound, the end like result and inequality in the bound, but I assume it's something like this, just because of the 2n. And the what I would say about getting bounds, here's the thing. When I tell you this trick, don't think that it's like obvious to do so. And if you see 2n, then you say, oh, then it's a plus b. Uh, That's all like a lot of intuitive stuff that you'll come up with when you solve problems. It will depend on how many problems did you solve and how well do you prepare yourself for problems. So it doesn't come from nothing. It comes actually from just solving a lot of questions. So when you look at my videos, the one part I want to single out is that don't think it's like a cheat code. It does help a lot. Like what I can say is my videos will help you a lot to improve. There's no doubt about that. But at the same time, don't think that you won't have to put in the work less or do less problems or ignore some stuff and think, oh, now I can solve P3s. No, you have to train a lot and do a lot of questions. I'm talking about what I'm basically doing is I'm trying to help you with your understanding of the problems, but uh, the skill of realizing at what point should you use what is solely dependent on how many problems did you solve previously. So, and I had a lot of questions in my DMs asking about what's the, do you have any advice on solving stuff? Do you have any like method? And I have two pieces of advice usually. First one, spam problems, just solve a lot of problems. And second of all, which is not very common, but try to create your own problems. So try to be like inventing your own problems and just exploring different constructions. Doesn't have to be from a problem, just on your own. That will help you like a lot. And I plan to make a video on the second method, but there were some technical issues with that. So maybe I'll make another video on that later. But okay, so we do have n squared plus a plus b plus 1, something like that, where ab equals n squared. And we kind of want to bound this thing. And yeah, so n squared. So first of all, n squared is obviously the squares we have here. So A and B are something to do with elements of the squares, something like adding on top to each square. So if we're trying to bound, what we're trying to essentially bound is, as I said, we try to use laser method. So the proof will be for sure involving around counting the sides around the square. So That's the laser method, basically. Laser method, when you shoot out four things and you try to count intersections, essentially it's just double counting this thing, the sides of the square. So, and here we get the idea that we have n squared plus a plus b plus 1, right? Take this space. Yeah. So here it's basically like this, minus 3. So n squared is obviously one square for one side per square. And then we have also a plus b, which are like something on top. And we do need to have ab equals n squared. And here we need to think about what do we know about boards as well. So boards, there are a couple of methods you can work with boards. And so there are obviously some like more local methods of uh, methods in how can you solve basically a board problem. But if we're narrowing it down to something broad, there are a couple of methods the way you can solve board problems. So board problems, they can have a couple of interpretations. So this is like a what I usually do. So boards, if you watched my mind map video, then you might know this stuff what I'm talking about. It's like a little mind map. So if we talk about interpretation of word problems, there are a couple. So first of all, there's just board. Second of all, there are graphs. So you interpret actually not just graphs, but you know what they're called. Not planar graphs. I think in English. Sorry. I forgot the name. Basically the graphs we bipartite graphs. Yeah, that's the name. Bipartite graphs. Yeah, bipartite graphs where you interpret each column and each row or each diagonal of one side and the other side as uh, separate part in the bipartite graph. Oh my goodness. Okay, and the other interpretation is permutation. So in bipartite graphs, okay, so if we look at interpretations, there's board, there's bipartite graphs, and there is permutation. And that's if we're talking about, this is in the case when we have like n by n board and chess rooks that don't hit each other. This is the case. So when you have n rooks, the usual interpretations are these two. So that's like kind of a reflex that you have. So this we cross out, and since we have like n squared that are not intersecting, there's kind of usually two ways you could go about it. Is bipartite graphs. So in bipartite graphs, the idea is that you want to say that if they're non-intersecting, then you basically have like cycle or just random just paired edges like this. So you can't have anything like this. So it's just pairs. And if it's a permutation though, the benefit of permutation. So why bipartite graphs are bad is because you bipartite graphs, they essentially ignore the order of columns and rows. So if I swap these two, the graph won't change, but the answer might. So this is like a hint that bipartite graphs are not the way to go. So the only way left is permutation if we want to interpret stuff. So, and permutation essentially it says we have uh, we have one thing, then we just interpret these things, these crosses, as our numbers, essentially. So, and basically, what we do want to claim is that we essentially in the permutation, it's the idea of a permutation is that you're given different coordinates, but you do know that all coordinates are present. So you have, if you look at a1, a2, an, that's 1. And then you look at its permutation, b1, right? Then you're given coordinates a1, b1, a2, b2, and so on, so on, so on. So that's the uh, permutation interpretation. And if you look at this and you look here, there is a subtle hint that we might use what is called Erdős-Sekres theorem. And this theorem states that if you have basically n squared elements, then you have or an r long chain or an s long empty chain if rs is less than is equal to n squared. And Dilworth's theorem says that if rs is exactly n squared and if r is n, s is n, or whatever, yeah, then they have a common element. So they do intersect somewhere. And here, if we look at this and this, we kind of want to try to use this theorem. And the way you do that is you interpret back. So what does it mean that you get a chain? So A1 is less than A2 and less than A5 and so on and so on. So on. So essentially that means you have like a path like this, and then you have a path like this, where by Dilworth, either there's an intersection or it's like strict inequality. But here we now see that we have n squared and we have the board basically split into 4 parts. And we're trying to bound the amount of rectangles needed. And again, the whole problem we have is solely revolving around these points, these n squared points. And you can try to get lost by just trying to bound this area on itself or this area on itself and so on and so on and so on. Never forget the answer, so keep that in head. And what we're actually trying to do, we're trying to do lasers and we're trying to count the amount of edges or something. So we're aiming on the amount of edges here. That's the only way we can get a proof. That's like, so if we have um, if at the end we have a answer or a proof, there's only one arrow going back, is like double counting edges of unit squares. And there's only one line here. Proof is a leaf, basically. That's the only way. So we're trying to find an arrow from here to here. We're trying to find an arrow, but we still are searching for it. So, yeah. And now, when you look at this, you do know that one chain is like A long, the other is B long, and essentially you want to, what we guess is that we want to add to every square here one more edge. And here also these ones do have to be included, so there's at least one edge. And what we need to do is we need to realize uh, we need to pick our edges not quite randomly. So for example, if I choose this edge and this edge, then what happens is, or no, there's a better example, this edge and this edge. We want to say in the ideal situation that every edge is covered by one rectangle, and then we can bound the amount of rectangles. So what we want to do is we want to bound rectangles, the amount of rectangles, by the amount of, or like this, edges. And because we don't have that much edges as a whole, we probably want one rectangle for one edge, not like one rectangle for two edge. And what comes down here is that this doesn't work. So this is bad. And we see that the only like at the same time, this pair and this pair don't work, this pair and this pair don't work. But if we look at this, at say this one and this one, they work fine. And same way here and here. So in here, you do come up with an idea. And the idea is that let's draw, so let's look at this square where they intersect and label one side blue. So we have this kind of direction up here. And let's label all of these sides blue, like this. And then let's take the red one, label this side, and label all these sides red. And then let's take a green side and do the same thing here. And then let's do finally the yellow one and look at all these ones. Note that what we get is that for every square, that is present on the board, so for every square, essentially there's one and exactly one rectangle that can cover. So every edge can be covered by at least and at most one rectangle. So no two edges can be covered by uh, one rectangle. And in total, you do get n squared plus a plus b. And then you also get here, so you have n squares, you get plus a plus b from both paths, and you should add 1 because we counted this twice, and we also counted the other sides. And yeah, and then you'd also note that these ones on the sides shouldn't be covered. So you do get a bound on this. So, and that's how we get our bound. So because these four shouldn't be covered, you do get that you just need n squared plus a plus b minus 3, and that's the answer that we wanted. And this is easily bounded, so that's the answer. And yeah, that's about it